Yes. We are in session 5, Robo Analyzer Software Exposure. We have our guest with us, Dr. Kumar Dala. Those sir already had a session yesterday. I would like to introduce him for the benefit of the new joiners. Let me take immense pleasure in introducing Speaker of the Day, Dr. Kumar Dala, Assistant Professor, NIT Jamshedpur. Dr. Vijay started his career as teaching assistant at IIT Bombay, worked in many technical institutions as assistant professor across the country. He completed his PhD from IIT Roorkee and his area of specialization is robotics. He has published research papers in various reputed journals and submitted many funded projects in the area of robotics. He is the member of Central Committee of Student Activities for Policy and Decision Making. He is professor in charge of Institute of Sports and Athletic Activities at NIT Jamshedpur. Welcome, sir, to the session, and over to you. The session is yours.
Yeah, thank you, ma'am, once again for your nice briefing about me. Am I audible, ma'am?
Yes, sir, you are audible.
Yeah. And once again, thank you, coordinator, sir, and other participants, faculty as faculty members, research scholars, and PG students. Once again, and actually, yesterday I delivered a lecture in. I used the software Robo Analyzer. Actually, AI in robotics that was scheduled yesterday, but what I found discussing Robo Analyzer, kinematics, dynamics will be more justified. That's why I delivered on those. So today I will I will expose my experience in AI in robotics. In my research, I used the genetic algorithm for optimizing energy and path of the robot. So now, and this with the permission of coordinator, I interchanged my topics. So today's my topic is uh, is it visible or need to I think just 1 minute. I think I need to share, na? Open share. Yeah, it might be visible.
Yes, sir, the screen is visible.
Yeah. So now I'm extending my work in the area of artificial intelligence. My mainly work was robotics in kinematics, dynamics, optimizations. I did a little work in optimization that now I'm extending and using AI in the robotics. I am not so much expert in AI, but what I did in my research that I can share you. Okay, so as I have also conducted many workshops and ATAL sponsored FDPs, 3 FDPs, 2 on robotics and 1 on AI. So with that experience, I'm going to start. Okay. Firstly, I would like to share what is the purpose of using this AI. So I want to share some videos, then I will link. It is a 6 degrees of freedom planar robot. The below one, this square in shape is the base of the robot, and other two objects, one in a hexagonal shape and the other is in square shape. Both are obstacles here. And this S curve is the Bezier curve. Bezier curve, once again. And this curve is the trajectory of the robot. So what I did, I divided my manipulator into two sections to avoid obstacles. As 6 degrees of freedom, then uh, 6 links are here. This is link 1, link 1, link 2, link 3, and other 3 links. So in this way, I divided the whole manipulator into two sections. Okay. So you can observe both sections are hitting the obstacles. Okay. So when I started my research, then I thought, can we use AI here? What is the scope of using AI here? So I found that we need to, here we are avoiding obstacles, and I put here circular barrier, virtual barrier in both obstacles. So what should be diameter of that circle? This was the one task. And what about my starting and end points are same? So can we optimize the path? The path means simply we use the path, sometimes the trajectories, but trajectories are more suitable word because path is the independent, the time independent, but trajectory is the time dependent. So better if you use the word trajectories, but sometimes we use path also. So our starting and last points are the same. So can we optimize this S curve, and not only this S curve, any curve? Okay. And then what will be the parameters to optimize? And can we also optimize the energy with this? Because in my case, I did research in space robotics. So in space robotics, what were the limitations? The main limitation was the onboard fuel. Okay. Suppose a robot is sent to the space with the satellite for the certain task like Chandrayaan 2. So that is especially time specific for suppose 10 years, 15 years. So we need to save our energy if for controlling all those things, if our energies consumes, then there may be a problem of shorten in the life of satellite robot. Okay, so why not to optimize energy? So with that three observations, I started my research. So again, I'm going to back to my PPT. Okay, this I will discuss how I avoided obstacles and how I minimized energies. And software exposure. Yeah. So what I did, a little bit about this software. This software is symbols, and this screen is a bond pad. It is based on the bond graph technique. And what is the bond graph technique? It is the graphical representation of any system. And here system is robotic system. So it is not only limited to robotics, other dynamic systems, hydraulics, electricals, uh, magnetics, all those we can model and simulate. Okay. So, and it is also freely available, not commercial. Earlier it was commercial. And what is the beauty of this? The beauty is we can easily write the kinematic inputs by drawing these graphical representations. Then the dynamic equations, the biggest task is deriving dynamic equations of the robots, especially in the case of very complex robotic system. Complex in the sense of having a more number of degrees of freedoms, having a more number of joints, various types like prismatics, revolutes. So that's why robot becomes very complex because it is a robotic system, a multi-body system. So if dynamics involved, only a robot is very difficult. Okay, so anyone can download this just to have feeling of modeling and a simulation of any robotic system. So what are the important I told with the only use of kinematic equations and this data based on these graphical representations, these windows come. Okay, these are the variables. Here we can write and we can define as per our convenience. Like aim 15 is what here. So just for M15, yeah. Please see where is our one M15. 15 is the board number. This 13 here you can see M15. This mass, yeah, inertia of the link. So for our convenience, what we have defined, M15 is equal to mass of link 3. link 3. Okay. And this also we can write here by using this text, because if a system is very complex, then we cannot easily identify like what is this I-15. So here, for simplification, we can write this will wrote in this way. We can write, and also we can change the orientation. We can use colors, and we can also change the font size. Okay, it is freely available, as I told you, so anyone can download. Okay, like suppose we are going to model before modeling any robotic system, we are going to model any spring mass system. Okay, spring mass system. Spring mass system like, see this one, or spring mass system card, you can like, yeah, this. And suppose we are going to model this, so what are the things required? And why not to type here bond graph model of spring mass system. Okay, so see in this, yeah, yeah, what happened? Just a moment. Yeah, see, it is a mass, a spring, and a damper here. So anybody, if suppose we take any body, so like this, and it behaves like a spring. That's why cage here, the spring constant. Okay, and it will also have some resistance. It will easily not deform. It will have some resistance. It will have some friction. So that's why we have put damper here, and here denoted by B. And it is a wall. Okay, it is suspended by a wall, and the mass is uh, here, means external force is applying on that body. Body here denoted by mass. Okay, how to model this using this bond graph? Okay, so what I did here, and see what are the source of energies here and the velocities. We are getting supplied force from only one source, external energy. Okay, so here, and what about the velocity? All elements, means the whole system will have some velocity. Suppose there will be some another like external force, so their velocity will be different. Okay, so one here denotes the equal velocity, and suppose there are 2, 3, 4 velocities, then for adding, what we need to do, we need to use the junction, 0, here junction 1. Okay, now 1 is what the velocity summation, sorry, it will have the equal velocity. Okay. Now, so that's why we have put 1 here. And as I told you, if there will be some another external energy or a force torque, so here we have to need to add that velocity. So we need to put a zero junction there. Okay. So now this force, time varying force, is here denoted by source of energy as E. And spring is here C. C denotes compliance. And what about this? As I told you, the anybody will have some resistance. So this it is denoted by resistance R. Okay. And what about this inertial element here? I inertial element either for mass or inertia we use. Okay. So this we can draw using this bond graph technique and software name is symbols. And software is developed by one of the great professor of IIT Kharagpur, Professor Amlendu Mukherjee. He is now no more, but he has developed this software and he has done a lot of research using this software. He had also wrote a nice book regarding this bond graph technique. Okay. So for that system, this is flow equalizing junction. Flow here is velocity. Okay. This I have taken from these drawing tools. Okay. Now what were the force over there? That's why I am taking source of effort. Okay. What about the spring were there? So that's why I'm taking the compliant element here. This we can put anywhere, no problem. Okay. What about the resistance? Resistance were there. Okay. So in that way, you can see. Okay. Yeah. CR, and also we need to take I, means we need to model I. Okay. Where is it? Yeah. I, we need to model. I is what? It is the initial element, denotes the mass or inertia. Okay. Now what we have to do? Like we have to connect, because it is a system and all the elements are connected by each other. That's why we need to connect it by this connections line. Okay. Now what we have to do? We have to give numbers. Okay. SER is now in this software will be denoted by R43. Okay, I41. And then we need to causalate. We need to give directions. Causality means किसकी वजह से क्या हो रहा है? What is the cause and the effect? So here cause is effort, effect is what? The motion, velocity. Okay. So in this way we can model any system. Okay. And further we can derive. This is it shows whether our system is correct or not. Okay. If there will be no errors, no warnings, then our system is correct. And from here, we can derive equations. Okay, and see here there are f terms. Okay, so with this we can easily, and this is the equations, this is the expressions according to our convenience we can denotes the variables. Okay, okay, then we can model and simulate, then ultimately we can animate, and by animation we got this. Okay, then what I did, I converted here the codes into the MATLAB language, because I need to apply a number of loops in my codes. So I was facing problem with this. So what I did, I converted it generates the C++ codes. Then I converted that into the MATLAB code. I made M file. Okay. What I did, I used the toolbox, genetic toolbox of MATLAB. Okay. Now, so this was a little bit another software exposure. Software name is symbol. Okay. Now I'm coming back to the my PPT, why it was required. Okay. So with the development of human space activities in area of space shuttle, spacecraft, and space station, space robot technology is paid more attention by many countries and researchers. The typical tasks to be performed by space robots are deploying or assembling space platforms, space stations, large antennas, solar power stations. It can be also used for servicing and maintenance of satellites, seizing and repairing of satellites in the space, capture and docking of objects, and for rescue operations, and there are more applications. Okay, so these are some robots developed by various countries like Japan, Canada, engineering test satellite. Okay, and this is the special purpose dexterous manipulator. Special purpose dexterous manipulator. So here dexterous means having redundancy, means having very large number of degrees of freedom. Okay, now this is this last one figure is space free flying robot. Why free flying? In space there will be no gravity and the base will be not fixed like industrial robot. Like KUKA robot, the base will be fixed, and whatever the vibrations felt during dealing with the objects will be absorbed by the ground, in the ground. Okay, but here the base is not fixed, so that's why whatever the vibrations will be there, it will be means not suppressed by ground, and its effect will be seen at the end effector motion. So that's why it is known as the space free flying robot. Okay. If someone asks the difference between the ground robot and a space robot, suppose a mobile robot. So in ground robot, the base is fixed. In mobile robot, like And there are also number of types of mobile robots, like wheeled mobile robots, wheel tracked mobile robots, like that. Okay. Also multi-legged mobile robots. And whatever the space robot, as I told, the base will be not fixed, and the body will be floating in the space. So what will be the problem? There will be a number of problems like generation of vibrations, and it will ultimately affect in the motion of robot tip trajectories. Okay. So for avoiding obstacles or minimizing a path, we need to opt the redundant robot. Okay. So what are the advantages? It can avoid obstacles. It can avoid kinematic singularities. It can work within the limit of joints. It can minimize energy consumption or needed motion torques. Okay. It can also optimize execution. I can increase dependability with respect to falls. Why dependability? Due to having a more number of joints, if any joint got failed, then we can use the other joints. Okay. So my focus is here, minimize energy consumption. Okay. But what are the other challenges? These were the merits, but what were the demerits of the hyper redundant manipulator? Okay, so it becomes bulky and complex due to more number of links, transmissions, actuators, sensors. The cost will be higher, and obviously the more complicated algorithms for inverse kinematics and motion control. Okay, so complicated algorithms will be generated, and taking care of that may be very difficult or time consuming. Okay. Okay. So here I am talking about collision-free trajectory of hyper-redundant space manipulator. So it is the schematic diagram. 6 degree of freedom robot in original configuration and a new configured state. So this colored one is in the original configuration, and the configuration is what? Orientation plus position of the manipulator. Orientations means the summation of angles, and position means the position of the end effectors or uh, uh, robot tips of each links. Okay. So here what I did, I converted these into 2 degrees of freedom. Okay. So that's why L14 and L47. The 6 links are converted into 2 links now for controlling the robot. Okay. And what was the problem actually? A robot 6 degrees of freedom will have a matrix of 6 columns. Okay. Uh, and but what about the that is the joint space means we are talking about the joints. Now, if you talk about the robot tip positions or velocities, so it is a planar robot. So here you can see only we have denoted x and y. Okay. So what will be one side? There will be a matrix of 6 columns, and another matrix will be of 2 columns. So we cannot multiply both the matrices. Okay. For that, there is one solution in the research. If you search, you will find the pseudo inverse of Jacobian. By using that, we can use, but that is also very complex. Okay, so what I did, why not to convert all the links into only 2 links? Okay, so that I did. And now the matrices, both the matrices for joint space and the Cartesian space. Cartesian means x, y means t positions. Joint space means talking about the joint orientations, theta 1, theta 2 here. Okay, and also here then the new angle will be theta 1n and the theta 4n. So here 2 dimensions for the joint and 2 dimensions for the tip trajectories. Okay. So the matrices will be now in square. Then we can multiply the matrices and we can get the final robot tip positions, velocities, accelerations, also the dynamic equations, forces, and the torques we can get. Okay. So, but here then I wrote kinematic equations of my new configured robot. Configured means its geometry will change. Okay, means the DH convention will be changed. Means its structure will be changed. Okay, so here the new robot tip positions X tip and Y tip. So for X tip, XCM, center of mass of the robot base, plus R cos phi up to here. This is the joint one is the root of the manipulators. Okay, root of here link 1. And before that, from center, the distance between the center of the robot base and the root of the link 1 or the manipulator is here. This distance is r cos phi. Okay, now how to get the t positions of this L14 means this link. Okay, so it is L14 cos phi plus theta 1n. Okay, we need to add this angle. This we can see here cos phi phi 1 and 1n. It is a cos phi plus a theta 1 plus theta 1n. Okay, in this way, I have modeled the kinematic equations for X tip and Y tip. Z I have not taken because it is a planar robot. Okay, and based on the original configuration, what I did, I got what is the X4 and the Y4 here. This X4, Y4. Okay. This I compared, and why I compared, because we need to get expression of theta 1n and theta 4n. So this I got this expression theta 1n I got, and how to get the theta 4n by equating the equations of original and new configured robot. So in that way, I got theta 4n, theta 4n, this one. Because geometrically it's okay, but we need to also express it mathematically. So some exercises are required, and this I got. Okay. Now, as I told, there were two obstacles, and then the nature of obstacles are static, and it may also dynamics. No problem. And the number of obstacles are used to, one is hexagonal and other is a square. Now, how to recognize is there any obstacles in the workspace? Okay, and what is the workspace? And the workspace is the work volume. Okay, or you can say where the robot can reach, the maximum reach of the robot, or you can say the working area of the robot. Okay, so whether there are obstacles or not in the workspace of the robot, so how to recognize that? So what I did, I used the pseudo distance criteria. Okay, and this criteria, the mathematical expression is this. This is a pseudo distance, and it is a function of xi and xi is what here the robot positions xi and effector positions. Okay, and further this what is this function? It is equal to xi minus xci, and xci is what the center coordinates of the obstacle. Okay, so by squaring and uh, adding the y, okay, and this taking this radius of what? Radius of this circle, this virtual barrier. Okay, then we can, by using this, we can recognize the obstacles. Okay. Uh, how, if this pseudo distance will be greater than 0, it means there is no collision in the workspace. And if it will be 0, then there may be possibility of collision. And if it will be less than 0, if it will have the negative value, then there is possibility of serious collision. Okay. So see in this one, in this schematic diagram, see these are the initial frames, and this is the frames, not initial but in between, and this is the final frame. Okay, means you can see final configuration to show the whether robots are hitting obstacles or not. That's why I have taken these two frames, two configurations. Okay, so you can observe both obstacles are being heated, which is not desired either for these obstacles or this manipulator. We need to say both. Okay, so see this one criteria here. This the pseudo distance is less than 0. Okay, means manipulator is going to enter this barrier. Okay, and see here, in this case it is greater than 0. Greater than 0 means both obstacles are being avoided. Now, our question is here, how much this greater than 0 is okay, but the working space, if it will be much greater, then what will be? There will be limited workspace for the robots. Okay, means then the robot cannot work freely in the workspace. So we need to take the optimal value of this pseudo distance. Okay. Exactly at this stage we don't know, means how much it is greater than 0, but how much, and which one will be the optimal one. So that can be done by using optimization techniques, uh, conventional or non-conventional, okay, like least square methods or some non-conventional genetic algorithms or some others. So genetic algorithm, it comes under the non-conventional, or you can say advanced technique of optimizations. Okay. So again, the recognition of obstacles. This concept extended for the proposed robot system as follows. Okay. Like stage 1, both the obstacles are hitting. Stage 2, only one obstacle is hitting. And stage 3, or both the obstacles are being avoided. So this is the stage 1, both the obstacles are hitting. And this is stage 2, one obstacle is avoided. In the stage 3, all means both obstacles are avoided. Okay, and these were the parameters taken for robot base and links, and also for controllers. Okay, this is a PID controllers and PD controllers, the KP, KI, KD values, okay, and PD values. Okay, now here we are actuating only two joints. Okay, so what we are doing, the other joints, we are restricting, we are locking the other joints by using the PD controller. So that's why this PD gain parameters using 500, 500, then we are able to lock, we are able to restrict those joints. Okay. And if you say, then why it will become redundant robot? Okay. So here what we are doing, we are starting with two joints, but in between we are replacing joints based on the energy consumption criteria. Means which joints are consuming less energies based on the optimization criteria. Okay, and these are the obstacle parameters for both obstacle 1 and obstacle 2. Okay, and also here the reference trajectories, control points, and these are the parameters. If you if you use genetic algorithms, so you need to take parameters like initial bound, means initial or lower or upper bound. Okay, so then the genetic algorithm will suggest like below, suppose this I have taken below, okay, uh, and upper values I have in between. Upper value I have suggested some like 3, and below value I have suggested like 1.5. Okay, So the that algorithm, genetic algorithm, suggested this 2.892 for this, and for these others like 1.115 are the optimal ones, and by using these we will optimize the energies. So with this, please allow me 2 minutes break, then we'll come back.
Participants, the feedback link for the session is there in the chat box. Kindly fill it. Feedback for the session link is there in the chat box. Kindly fill it.
Yeah. So I have shared one link to the coordinator, and the coordinators are also shared to you. Please go through.
So I shared it in their WhatsApp group as well as in the chat box here.
Okay. So these you can access. It will take only how many questions? 15 questions. So only 5 minutes it will take. And once after submitting, you will know your scores. However, in this today's part is not in this test. Mainly the Roman analyzer part is here. Okay. Okay. Then shall I continue? Okay.
Yes, please.
Yeah. Okay. So how to validate that pseudo distance as I told you, and I also told you that that pseudo distance. I am not going to show the MATLAB what I use. You know what is the problem? The those who are not commercial, that softwares I am showing. But MATLAB, you know, I'm not showing here. But I used a toolbox of MATLAB for genetic algorithm. So you can use uh, software and you can go through the toolbox. Okay, and you need to make the objective function. That's the biggest task. Making objective functions and making some variables like constants and making constants like variables, that are the biggest challenge. Okay, so this pseudo distance, how to validate that? Mathematically it's okay, but graphically how? So see, in stage 1 and 0 is the suppose a limiting point, you can say. Below 0 and above 0, see here, focus on below 0. So this curve 1 for optical 1, okay, it is within this 10 to 20 seconds, it is reaching, entering in the into the barrier of circular barrier of optical 1. Optical 2 at the last, between 50 in between the 57 to 60 seconds, it is entering into the that virtual barrier of obstacle 2. So it shows both means hitting the, both obstacles are hitting to the manipulator. Okay, but observe this curve here. The curve, this solid line curve is not going below the 0 value. Okay, but obstacle 2 here, it is going below 0, means reaching into the barrier of circular barrier of obstacle 2. Okay, that's why here obstacle 2 is hitting to the manipulator. Okay, now see this stage 3, this one, stage 3, and focus the curve. It is theta versus time. Okay, means joint velocity, theta, joint position versus time. So see here, And also what we are doing here in between, to avoid obstacles. Suppose a corresponding joint is due to corresponding joint, our manipulator is going or just near to the obstacle, then we are locking that joint and releasing the another joints. Okay, and that these are based on the sensors. Based on the sensors inputs. Okay. So see here in this, none of the curve going down to the zero value. Stage 3, yeah. This is, yeah. Stage, no, it is a joint rotation. There is one more, that pseudo distance, this one. Yeah, this one. See, both are above zero curve. It means both are not hitting to the manipulator. Now this trajectory, this part we have done now, avoiding obstacles. But primary and the secondary things. Secondary was the avoiding obstacles of free trajectory motion, free collision motions, and the primary task is always the trajectory planning. Okay, to reach the object from one point to the another point. Okay, accurately, that is our the primary task, and avoiding obstacles in between in the workspace is the secondary task. So our primary task, whether our primary task is means accurate or not. So in this case, in stage 1 it is accurate. In stage 2, due to it is not this dotted line is the reference curve. Reference trajectories means that the robot must follow these trajectories. But see what is happening here. First section, first half is okay, but in the second half, it is not following the given path. So it is not the means recommended. But in the stage 3, what is happening? And see what we are doing. In up to this, we are choosing joints 1 and 4. And as I told you, these joints are chosen as based on the minimum energy consumption. Okay, like why we have chosen 1 4? Why we have not chosen 1 5? Because 1 4 is a pair of joints. 1 4 is consuming less power. Okay, then in between what we did, we replaced joint 1 by 6. Okay, and then at last here 4 out of 4 6, joint 4 is replaced by 1. In this way we are getting the accurate trajectories. Okay, so these are the joint rotations, and it is animation results. Animation results are not different. It is from simulation. Based on the data, on the simulations, we get this. Okay, that I have shown in that videos. So what I shown, this is stage 1. Okay, in stage 1, stage 2, stage 3, what is happening? Both obstacles are hitting, but in 2 only obstacle 2 is hitting, but in stage 3 no one obstacle is hitting to the manipulator. It can be further visualized by this animation video. And the software is now non-commercial, so anyone can download, and it works on the numerical methods. You might be knowing in numerical methods do not give the exact solution. Okay, some approximate values. Okay, now see the second stage. What is happening? Robot 1 didn't hit to the manipulator, but see, it is struggling in between. The robot is struggling in between, but ultimately it collided to the manipulator. Now stage 3. It is the first section of the robot is going to reach to the obstacle 1, but it is stopped and it didn't hit. Now focus on the second section of the manipulator, and half of that trajectory is completed. Now see, in between the joints are being changed based on the sensors outputs. Once again, again okay. In this way, have avoided obstacles. Okay. I have one more video that is also my work, and since it is FDP and robotics, then that's why I'm showing it. See, there are 3 robots in working in cooperative mode. Okay, once again, and middle one is the hackjack object. It is not obstacle here. It is object, and the object is being manipulated by the robots. 3 robots, 3 space robots. Okay, and see, observe why I'm calling it space robots. Observe the bases, how bases are moving. It will not happen in the case of like a Kuka robot in any Puma or any Tata's robot. It will not means not in any industrial robots, because the base will be fixed. So whatever vibrations will be absorbed by the ground. Okay. Okay. Coming back to the PPT, this now reconfiguration and trajectory tracking optimization. Okay. So as I told you, again reconfigurations. Then there are 3 aspects in this. A control strategies based on the minimum power criteria when all joints are in healthy condition. Okay. And second, the redundancy exploitation to reconfigure the space robot in case of failure. And this third one, workspace trajectory optimization using genetic algorithm. Okay. So These were the out of 6 joints. If we use only 2 joints, then there will be total 15. Serial number 15 possibilities of having a pair of joints like 1, 2, 1, 3, 1, 4, 1, 5, and so on. Okay. And as I told, it is an integrated integration of bond graph technique and MATLAB. I mean, integrated means that bond graph, the codes generated in symbol software that that is in C++ is converted into MATLAB language, and the file is then saved in M file. Okay. This bond graph technique generates. Yeah, bond graph technique generates state equations and the user defined equations in form of C++. Okay. State equations means in the form of variables like variables maybe like we have a string, and what will be our variable will be our that displacement or sub variables in terms of forces and torques. Okay. And what about the objective function? This was the objective function, the total power, and it is a function of torques. Okay, a function of torques and angular velocities. So you can see there are 6 number of angular velocities, and this tau 1 and tau 1 uh, describe. This is a as I told, for controlling joints, we are using PD controllers. Okay, so when we have to release this torque, okay, when not to release, that's why we have put here the tau prime. Okay, this can be visualized in. No, there is a no bond graph model. Okay, but it can be seen that in that bond graph model. Yeah, I can also show it. Okay, let me do it. When I open the actual model, controllers, this one, not here. I didn't find it. Okay, let me again search it. This optical avoidance. Yeah, here this TF. I'm putting like switches here. Okay, whether we have to switch on or switch off means switching on means we are releasing the joints for actuating, and switching off means we are locking that particular joints. Okay, so MATLAB results of total power for 15 possible configurations. See, you can see the 15 possibilities and total power consumptions. pair of joints 3 and 5 consumes least power of energy. Okay, so this is again I used a genetic algorithm here, and I make variables are all controlling parameters like PID gain parameters, PD gain parameters, and these the control points of the these reference trajectories. So in this, there were 4 control points in the starting, ending, and in between this node of this upper section and the below sections. Okay. And suppose this is in case of failure. So here I'm not going to detail about the failures. Okay, and this optimization technique, this is a flow chart of the GA implementation. Okay, it starts with uh, entering number of generations, population size, crossover, and mutation probabilities, number of variables, lower and upper bounds of variables. These we need to give. Enter number of generations. So I took 100. Okay, and initialize population. Then evaluate the population for minimum energy calculation by numerical integration of state equations. Then assign fitness to population. Has the process converged? Means did we get the have we been suggested the optimal values for the parameters or not? If suggested, then okay, yes, then stop. If energy is not minimized, then again we need to process, again evaluate, means if not, then reproduction, crossover, mutation, then this again the process is uh, uh, repeated till we don't reach the optimal values. Okay. So see here in there are three figures. In the first figure C, there are two S curves, and starting and end points are same, but uh, the middle sections are different, middle points are different. So you can see this is this one you can see point of failure and the reconfiguration and optimized trajectories. Yeah, this optimized trajectories are on the inputs of the genetic algorithms. Okay, and then you can observe this second figure, the power versus time, and this red color denotes optimized one, and these dotted lines denotes non-optimized. So optimized one is consuming less energy, and which were our desired, means which is our expected results. Okay, and see the final animation of the uh, robot motion. You can see this is the animation. Okay, and I regarding what is the genetic algorithm and direct search toolbox. So in this way, you can I can share this. You can access how to make objective functions, writing an M file, and how to interface uh, objective functions with our codes And this is the window. To open the genetic algorithm tool, enter GA tool at the MATLAB command prompt. This you can do, and see some newspaper cuttings regarding robots. It is not a human versus robot. Okay, robots are being used for assisting the humans, like uh, paralyzed people, or for surgical work. And there are many applications, like we cannot reach in the space, but a robot can go and can do the task of servicing, maintaining the parts, and it also can handle like hot objects, which we cannot do. Okay. Uh, Regarding application of this robotics and AI, you might be knowing this Sophia. It is a humanoid robot, and now it became the first robot to be granted citizenship in the world. Okay, it is a newspaper that times news. So it is a citizen of now Saudi Arabia. Okay, this we can okay. Humanoid robots Sophia said to win many a heart. It was invited in Visakhapatnam during Visakhapatnam in a Vijay FinTech Festival. And the recent applications of AI, see in this, it is also from a newspaper, robots to serve food at Bhubaneswar's restaurant, robot chef in Odisha. And also they are saying that 5 innovative robots will be in the news, serve food at restaurant, teach yoga, and shift heavy furniture in a pinch. And others like humanoids to perform experiments in space before human beings. Okay. And see, Milagro ne utara Kamkaji robots, and there are a number of applications. Nowadays, robots are being used in the COVID-19. Our India also, and the other countries like South Korea's various robots are the most popular. These UVD robots are being used, and these are some technologies to combat COVID-19 and how the various countries are using this. So with this, I would like to say thank you to all the coordinators and dear faculty members, participants, research scholars, and obviously I'm very thankful to uh, KCG College of Engineering for giving me this opportunity. I'm not so much expert. I'm still learning, and I'm trying to learn more and more. Now I'm expanding my research in the area of artificial intelligence. I'm not so much expert. I'm still learning, and in the near future, if we want, if required, we can collaborate with not only coordinators, all the participants. Uh, I'm always welcome. You can search my name in Google, Vijay Kumar Dalla. Then you will find my biodata. So my number is also there. WhatsApp number. You can contact me. My email ID is also there. You can contact me regarding any issues. regarding any projects related to robotics. If required, then definitely I'm here to serve you. With this, thank you all. Thank you, sir. If any queries or any discussions, please let me know, and it is open for all.
Thank you, sir. Participants, any queries? Participants, you can unmute your mic and answer and ask your query.
Thank you, sir. Nice presentation, sir.
Yeah, thank you, ma'am.
Thank you.
Thank you, sir.
And please share some screenshots. I usually update in what's in my Facebook. So if you have any screenshots, please share me.
Thank you, sir.
Professor, I have one simple question. May I ask?
Yeah.
Okay. Say, actually, I'm not. I don't have any background from. I'm not from mechanical or CAD CAM anything. I'm from software engineering. This question is: we use robot. The robot can talk, walk, can run, can pick something from the ground, right? So these things which all are involves lot of motion, different angles. Am I correct? In such a case, which is the hardest thing for a robot to perform these things with respect to kinematics?
Which is?
Which is the hardest part of thing to perform by the robot? Either
Yeah,
talking.
nowadays the biggest task is not that kinematics or dynamics. Yeah, obviously controlling dynamics is the biggest task. Controlling,
Okay.
having a more number of joints is the biggest task to be controlled, and definitely the emotions parts, decision parts. Eh, when the robot had to take decisions, the best decision, that is the biggest task. Means a robot will take uh, based on the situations, whether it can react with the situations or not. That is the biggest task.
Okay. Thank you, sir. Thank you. Participants, do you have any queries?
You can put it in the chat box also if you have any queries. We will take it forward.
Yeah. What about taste? How it was? Please let me know. Regarding this taste.
Yeah. Yeah. The people are doing that test, sir. Yeah. They did. Yeah.
Yeah. However, I can see here.
Yeah.
I can see the marks.
The participant posted one message in their groups. It was very nice, simple questions, and one participant scored more than 11 marks out of 15.
Yeah, good, sir.
Okay.
One
Please.
one thing. I always recognize my parents.
Yeah.
I would like to say it may be like a motivational talks to all. Like I have put the things in my CV and it is in the website of our institute in IIT Jamshedpur. All those what I am doing, what I am learning, what I am getting chance to interact with the people like you. Already you are you have a potentials, and in front of you I am sharing my knowledge with the grace of my parents. This I have expressed here. Words cannot express the feeling I have for my parents. Late is no more. My father and mother for their sincere prayers, constant encouragement, and blessings. They have sacrificed a lot for my basic education, which made foundation for my life, for my today, followed by engineering study with a PhD degree. They used to migrate from Chhattisgarh, I am from Chhattisgarh, to other states for brick making work as a laborer for my basic education. Even here at Tatanagar, I am at Tatanagar, Jamshedpur. So putting it in sewage, however, not standard practice, but I believe that it may inspire some uh, participants, students. So, and still I'm learning. So with this, thank you.
Thank you, sir.
Thank you, sir. That was so touching. Shankar sir, shall we
Yes,
wind up
ma'am.
the session? Yes.
Wonderful.
Okay.
Thank you.
Okay. So, on behalf of KCG College of Technology and Department of Computer Science and Engineering, I would like to thank Dr. Kumar Dala for giving an excellent coverage to the topic Robo Analyzer Software Exposure. Thank you so much, sir, and looking forward to attend many of your future sessions. God
Yeah,
bless you. Thank you, sir.
yeah, thank you, ma'am. Thank you, sir.
Thank you, sir.